I welcome Joel Primack.
Thanks, Eric. It's a pleasure to be here. I'm going to talk about basically an introduction to modern cosmology and the simulation game. And I'm going to mention that the ideas we used to have about how galaxies form and evolve were basically wrong. When we actually got to see what the galaxies look like, starting with the installation of a new camera that gave us infrared capability on Hubble Space Telescope in 2009, we actually saw what galaxies look like when they start, and we were all shocked. But our simulations look a lot like these images that we're now getting from Hubble, so we're beginning to figure it out. And one of the ways that we are hoping to improve our understanding is using deep learning technology. So to start with, just to get the terminology understood, we live in the solar system. Earth is 8 light minutes from the sun. Jupiter's 40 light minutes, Saturn's 80 light minutes. The entire solar system is less than a light day across. The Milky Way, our home galaxy, is 100,000 light years across, the visible part of the Milky Way, and we live about a quarter of, about half the way out, about 25,000 light years away from the center. Our galaxy is part of what we call the local, or the Virgo supercluster, the nearest 10,000 or so galaxies. There's a cluster called the Virgo cluster, which is the densest group of galaxies in 100 million light years around. But this is a fairly small part of the universe. On the really large scale of billions of light years, we've surveyed the universe and we've discovered that the universe has a lot of structure. So the other thing we've learned is that the visible universe is just a tiny fraction of the universe that's really out there. What we see represents about half of 1%. So most of the universe, as far as the energy and matter content, is dark energy, about 70%. About 25% is a mysterious stuff that we call cold dark matter, a theory that, as Eric said, I helped to create and develop. We don't know what it is, but we know how it behaves. Cold means that it was moving very sluggishly in the early universe, and of course that term sluggish, which my collaborator George Blumenthal, now the Chancellor of UC Santa Cruz, and I always use, is a call out to our mascot at Santa Cruz, the banana slug. All the atoms are about 5%. The invisible atoms are about 4.5%. The visible stuff, the stars and glowing gas clouds, is about 0.5% of cosmic density. And the stuff we're made of, all other atoms besides hydrogen and helium, is about 1/100th of 1%. So we and Earth are extremely rare parts of the universe. They're not typical at all. So we call this the double dark theory, or technically lambda CDM, lambda, Einstein's representation for dark energy, and cold dark matter. So dark matter and dark energy. Imagine the entire universe is an ocean of dark energy. On that ocean sail billions of ghostly ships made of dark matter. But we don't see the ocean, we don't see the ships, we just see the lights on the tops of the tallest masts of the biggest ships. Those are the galaxies. Now, how do we know that this is true? And the answer is the theory made all kinds of predictions that were subsequently confirmed in fantastic detail. For example, this is the green curve is the predicted distribution of fluctuations in temperature in the cosmic background radiation. This is the map of the whole sky as seen by the Planck satellite, our latest instrument for this. And every one of these little red points is an independent measurement. And the agreement is absolutely spectacular. And this is the temperature polarization data, the polarization data. And also, for the large-scale distribution of the galaxies, it's a similar story. As we look out in space, we're looking back in time because we see light that left longer ago when we look farther out. So we're seeing those galaxies as they were longer and longer ago. Nearby galaxies like our own Milky Way, we see on the scale of 100,000 years ago, nearby stars a few years ago. As you look further out, this first sphere represents the period when Earth and the Sun formed about 4.5 billion years ago. And the next sphere represents when big galaxies like the Milky Way took more or less their present shape. So these galaxies look like nearby galaxies. They're not very different. But if you look beyond, that's about 10 billion years ago. If you look beyond that, the galaxies look very different indeed. These are all images from Hubble Space Telescope. And one of the things you'll notice is that they're not very round. And that's turned out to be the common understanding. And beyond the visible galaxies is this cosmic dark ages, where galaxies haven't yet formed enough stars for us to see them. We'll start to see a little further into this when James Webb Space Telescope gets launched next year. Then the cosmic background radiation, this colorful sphere, and the Big Bang itself. Now, simulations allow theorists to make metaphorical or real movies of how the universe evolves. The astronomers basically just give us snapshots. We don't get to see how galaxies evolve because they evolve on a time scale of hundreds of thousands of years to hundreds of millions or even billions of years. Cosmological dark matter simulations show large-scale structure and the properties of the lumps of dark matter that we call halos. And then we can try to put galaxies into those. If you look at a galaxy, the part that you see is just a tiny little fraction of the full galaxy that's actually there. So this is a dark matter halo of a galaxy like the Milky Way, with these big lumps hosting satellites, and the smaller lumps invisible, but maybe having effects that we can see, for example, in gravitational lensing. How does this fit into the large-scale structure? More or less like this. So this is a slice from one of our big simulations that we ran next door at NASA Ames Research Center on the biggest NASA computer, which is called Pleiades. This one took about 2 months using about 14,000 cores on Pleiades. And we've run a bunch of these big simulations. So let's zoom in on a little piece of this big simulation. It's only about 1,000th of the size of the simulation itself. So this is what the distribution of dark matter halos looks like. What you see is a rich cluster, a cluster with thousands of galaxies, would be hosted by this big lump of dark matter. The white areas are regions with a lot of dark matter. And these big clumps form where these filaments cross. The dark matter is spread out along these long linear structures that we call filaments. And galaxies really are distributed primarily in these long linear structures, just as the theory predicts. Now, how did this massive cluster halo form? We keep track when we run the big simulations of every single particle, many billion particles, and every dark matter halo. And all of the things you see here, the thousands of halos, each of which will be hosting galaxies or maybe several galaxies, are going to end up in that one structure, that big central one. Notice that they're not spherical, they're elongated. The earlier they form and the more massive they are, the more elongated they are. As these halos accrete, they change their shape, and what we're doing is playing you the video based on storing about 200 time steps as the big simulation ran. So that's the dark matter halo. Of course, all of that substructure continues to exist inside that halo and the galaxies. So we try to understand in detail how stars form in galaxies. A couple years ago, last year I guess is when it finally came out, we published this paper suggesting that maybe the way the dark matter halos accrete matter is what's really controlling star formation in at least many of the dark matter halos hosting star-forming galaxies. We called this stellar halo accretion rate coevolution, or SHARC for short. There's a kind of model that theorists make that we call bathtub models of galaxy formation. And of course, I put the shark in the bathtub. So we came up with that clever name so people would remember it. Now, I need to tell you, to explain this story, two basic facts about galaxies. And this will also, I think, give you an idea of some regularities that we're learning about how galaxies work. So one is the stellar mass to halo mass ratio as a function of halo mass. Milky Way is about a 10 to the 12 solar mass object. So Milky Way is right around here. And that means that about 2 or 3% of the mass of the Milky Way is stars. You might have thought it was more. But that's as much as you ever get. Lower mass galaxies and higher mass galaxies have an even smaller fraction of their mass in stars. And also, it's pretty much independent of redshift. These are values of different redshifts. Redshift corresponds to time back in the history of the universe. But it's a strong function of the mass. Now, the other thing is that galaxies form stars at a rate that's largely governed by the stellar mass of the galaxy and the redshift. So this is what it is for nearby galaxies and more distant galaxies. This is the mass, the stellar mass of the galaxy, and the star formation rate, number of stars formed per year, stellar mass formed per year. And what you see is that at least the lower mass end is pretty much proportional to this plot, which is the star formation rate just growing linearly with the mass. So the rate at which galaxies form stars is largely regulated by the stellar mass of the galaxy, and it's a little bit higher at high redshift than at low redshift, about an order of magnitude higher at redshift 2.5. So two basic facts about how galaxies work. And what we noticed when we looked at these big simulations is that the dispersion, so we noticed that the accretion rate grows like this, so it grows by about this order of magnitude as you go out in redshift, and the dispersion is independent of mass and independent of redshift. And the dispersion in the star formation rate of galaxies is known to be about 0.3 dex, in other words, a factor of 2 up or down. Most of the stars in the universe form at rates that are really controlled by the stellar mass of the galaxy. And there's a simple derivation that shows that the rate at which stars form, as long as there isn't much change in the star, in that plot that I showed you a minute ago, this plot, which is stellar mass versus halo mass, if there isn't much change with redshift, then it's going to be governed by this term. So the star formation rate, dm star dt, is dm star dm halo dt. That's the accretion rate. And that allowed us to predict what the star formation rate should be across more than an order of magnitude in stellar mass and back to redshift 4, even higher. So back over most of the history of the universe, and it actually works remarkably well. Now I want to move on to understanding, so that's something about how the large-scale structure of the universe relates to star formation in individual galaxies. This is an astronaut installing this amazing instrument in Hubble Space Telescope. They took out an old instrument that doesn't work anymore, or that wasn't working so well, Wide Field Camera 2, and they replaced it with Wide Field Camera 3, which for the first time gave us these huge Hubble images, sharp from edge to edge, in the infrared. And before Wide Field Camera 3 was installed, we only had images like this of forming galaxies. All we were seeing was ultraviolet light, which is emitted by the stars that have just recently formed. You get a few very massive stars which put out a lot of their light in the ultraviolet. And then that gets redshifted so that Hubble could see it in visible wavelengths. But to see the full stellar populations, you have to see the infrared. And that's what we now could do. These are the same galaxies. And you can see that with the infrared capability, we're seeing a lot more. So that's the basis of my saying that now we can see what galaxies look like when they were forming. Back to redshifts 2.3 for red light and 3 for blue light, that's about 10 to 12 billion years ago. So we can see the galaxies. Of course, the universe starts at 13.7 or 13.8 billion years ago. So the first couple billion years, we're going to have to depend on James Webb Space Telescope, which goes up next year to illuminate. So the Candels program was the program that succeeded. There was a big competition, and we at Santa Cruz were part of the winning team. My colleague David Koo is an astronomer, I'm a theorist, who are part of the CANDELS team. And that's Cosmic Assembly Near Infrared Deep Extragalactic Legacy Survey. I think David first came up with the CANDELS acronym and then came up with a... Anyway, so we're focusing on this period when stars mostly formed in the universe, the first 5 billion years or so. That's Redshift 2, about 3 billion years after the Big Bang. Redshift 3, less than 2 billion years after the Big Bang. That's the peak of star formation. That's when the galaxies really formed. So to understand galaxy formation, we do what we call hydrodynamic simulations, where we follow the gas and not just the dark matter. And the gas turns into stars. Some of the gas ends up as supermassive black holes at the centers of the galaxies. And of course, there's a huge amount of energy output by the stars. Sometimes they explode, more energy output. The supermassive black holes, as they accrete, a lot more energy output. And we're trying to follow how all of this stuff is happening. There's basically two approaches. Low resolution approaches, kiloparsec, that's about 3,000 light years. Small compared to the size of a galaxy, but very large compared to the regions where stars actually form. And then much higher resolution, tens of parsecs, so that's 100 elements compared to these, and that's 100 cubed because it's 100 in each of the 3 dimensions. So these are much more expensive simulations. These simulations cost 100,000 to 1,000,000 CPU hours per galaxy. These simulations cost 10 or 20 million CPU hours, and you get tens of thousands of galaxies, but at much lower resolution. And we're actually using both of these to compare to the observations. I tend to emphasize these because we try to be as self-consistent as possible in these simulations. So these are examples from our simulations. That's a face-on image. You're seeing the gas, and there's the stars. This is what it would look like to a telescope. This is the same galaxy seen edge-on, so you see it's really a disk. And there it is, edge-on. And this is that same galaxy, face-on, edge-on and face-on. And these are 2 different observed galaxies at Redshift 2, about 10 billion years ago. And you're supposed to notice that they look a lot like the simulated galaxies. Notice that they're very clumpy. We've run the simulations several times. We run typically 35 simulations at a time, each one costing between 100,000 and 1,000,000 CPU hours per simulation. I get tens of millions of CPU hours from Google and from NASA Ames and other places. So this is some simulations that we don't like so much anymore because it turns out that the galaxies really are elongated and they don't have as many stars as these simulations did at the same redshift. These are a better match to the observations. This is what these would look like if you could see them close up. This is what Hubble would see. And these are the infrared images. So Hubble has seen 3 different phenomena. We have interpreted the Hubble images to see these 3 different phenomena. So one is that galaxies start down here. Star formation rate is increasing downward, and the compactness of the galaxy is increasing to the right. So they start not very compact. Some of them become very compact, very, very dense, very rapidly moving stars and gas. And then they also have a large fraction of these galaxies have active galactic nuclei, quasars, supermassive black holes accreting like crazy. And after only a few 100 million years, which is a short time for galaxies, they quench. That is, they stop forming stars. So the star formation rate goes way down, which is up in this diagram. And then they grow a little bit in size. A lot of other galaxies are what we call the slow track. We called this the fast track in this paper published in 2013. There have been a number of follow-up papers. And those are galaxies that never entered this compact, rapidly star-forming part of the diagram. They just slowly grow in size but fade out. In our simulations, we have some slow track, we have some fast track. These are organized the same way as the picture. We can follow in the individual simulations this is the inner part of the galaxy, the very center part of the galaxy. And we notice that the center part of the galaxy is mostly dark matter until what we call a compaction event occurs. A lot of gas flows into the center. There's the gas flowing into the center. And it becomes stars. And so the rapid conversion of gas into stars depletes the gas, and then also it drives some gas out. All these energetic processes in the center, including the supermassive black hole. And unfortunately, we couldn't include the supermassive black holes in these simulations, so we haven't figured out enough about how they really work. So gas flows in, and then it flows out. And in the inner region of the galaxy, this is what's happening. In the whole galaxy, that's pretty much the whole galaxy. That's out to 30,000 light years, so bigger than that size of the Milky Way. Further out than we are, anyway. So you see that the dark matter still dominates. The stars grow, although they're not growing in the center. The stellar mass is constant in the center, but in the larger galaxy, the stars continue to grow. So how does this work when we actually look at our individual simulations? So this is going to show you how a simulation evolves, and we're going to track the dark matter, the stars in red, and the gas in blue. And this is in the inner 5 kiloparsecs, so that's about this big. And this is the inner kiloparsec. That's about just that very central region. So this is stars and gas face on, gas and stars edge on. Here goes. So you see that there's a compaction event about to occur. A bunch of gas just flowed into the center. And the center is now becoming much rounder. It was elongated before. So, and now you're seeing this nice spiral structure and a nice disk. Now, the observers, when they looked at this Candel's program, when we looked at the distribution of the axis ratio, so on the sky you can see an image that's got a long axis and a short axis, and you can take the ratio, short axis over long axis, and if you plot the histogram, it looks like this. This is for galaxies between redshift 1.5 and 2, so that's going back. Redshift 2 is about 10 or 11 billion years ago. Redshift 1.5 is a couple billion years closer. So this is very much the period when galaxies are forming. And what you see is that the distribution for these lower mass galaxies and also intermediate mass galaxies is an inverted V. It peaks at around 0.3. So axis ratio 0.3. So basically long axis more than 3 times longer than the short axis. And there are very few up here near 1. Now, a spheroid is going to look like an axis ratio of 1 no matter how you look at it. You're going to catch galaxies in every orientation. A disk is going to look like axis ratio close to 1 face on. It'll be as 0.2 or something, whatever the thickness of the disk is, edge on, and everything in between more or less equally likely. We're just not catching very many near 1. So that means that a majority have to be these elongated objects. And very few are spheroidal, and not very large fraction are disky. They're mostly these elongated objects. So we used to think that galaxies are a mixture of disks and spheroids, like nearby galaxies, sometimes with a spheroid in the middle. But actually, when they start, galaxies look like pickles. And our simulations are showing exactly that same phenomenon. There's the dark matter, there's the stars aligned with the dark matter. This is from the paper that we published on this. So the paper that really established that this is what the images look like was led by Candel's astronomer, published in 2014. And our theory paper explaining it, the first of our papers, came out in 2015. So there's the stars and dark matter highly aligned. This is looking down the long axis, so now they look round. And again, the dark matter and stars are very aligned. And they're elongated. On the left-hand side of this diagram, the stellar mass is less than the dark matter mass in the center of the galaxy. On the right-hand side, the stellar mass is the dominant part. More star dominated, more dark matter dominated on this side. And when it's star dominated, you see that the galaxies are becoming round. These are round, these are elongated. So that's just like what the images showed. And we published a much more detailed paper led by a postdoc, Michele Tomasetti. And what we found was that essentially all galaxies go through this elongated phase. So the ones we saw out to redshift 2.5 or 3 with Hubble were just galaxies that ended up a little smaller than the Milky Way. The Milky Way would have gone through that stage, we think, at redshifts between 3 and 4, and that's what James Webb Space Telescope is going to let us see. So we're predicting that the vast majority of galaxies that James Webb lets us see out at the higher redshift are going to be these elongated things. We don't know if that's true. We'll find out in about a couple of years. So I'm now near the end of the talk, and I'm going to talk a little bit about where we're using deep learning. So Sander Dieleman, who was then a graduate student at the University of Guelph in Belgium, and is now at Google DeepMind in London, he used a deep learning code to predict how Galaxy Zoo, a citizen science project, classified nearby galaxy images. And he was able to predict the Galaxy Zoo classification with 99% accuracy. And he won a CAGO competition in the machine learning community in 2014. Mark Huerta's company used Dieleman's code to classify Candel's galaxies. So these are our galaxies out in the period when galaxies are forming. About 8,000 of them had been classified by a team of about 65 astronomers. That was used as a training set in order to get enough to be a useful training set and not overfit the data. He had to rotate them and also change the colors a little bit to get about 60,000. And so Mark Huerta's company also had to do something similar with the Candel's galaxies. And she's published a big catalog. So only one of the fields, Candel's is 5 different fields, only one of the different regions of the sky that Candel's used had the galaxies classified. And so once the machine was able to classify the galaxies as well as any astronomer, Mark was able to classify all of the galaxies. And then he was able to study how the galaxies have changed in their appearance since redshift 3. So that paper was published last year. With support from Google, Mark Huerta's company has visited UCSC last summer, briefly last spring, and will again be back this summer. And his grad student, Fernando Caro, Fernando, would you raise your hand? So he's been visiting us since March and will be through mid-August this summer. And we're working together to try to understand galaxy formation better using deep learning. And the people whose names are in blue here are here today. And then we have 2 other deep learning projects that I'll tell you about, trying to understand better the galaxy environment out at fairly large redshifts, so the more distant galaxies, where we mostly only have very rough estimates of how far away the galaxies are. And also looking for the big clouds of neutral hydrogen in Sloan Digital Sky Survey spectra. So this is just a short summary of what Sander Dieleman did. It's based on his sort of blog entry here, my solution for the Galaxy Zoo challenge. So this was a flow chart of how Galaxy Zoo works. People are given an image and they're asked to classify it into disky or more roundy, and then if they answer this, then they go down this part. If they answer this way, they go down this part. If you count all the different boxes here, there's a total of 37. So they get 37 possible choices, although it's a decision tree, so they only go down one side. And the game in the Kaggle competition was to predict all 37 as accurately as possible. So they were given, I forget, 100,000 images or something, and they could use some of them as a training set and then some of them as a confirmation set. And what Sander Dieleman did was to construct a deep learning network. He actually constructed 16 different ones, training them slightly differently, and then he polled them to get the best estimate. And he ended up actually getting 99% right. So it was really quite amazing. Although he's a machine learning guy, he published a nice paper along with Willett, who's the leader of this Galaxy Zoo project, in Monthly Notices of the Royal Astronomical Society, one of the 2 leading astronomy journals. So it was basically the same sort of deep learning code that Mark Werda's company used to classify the Candel's galaxy images. So we mimic human perception with deep learning using convolutional neural networks trained to reproduce the Candel's visual morphological classification based on the 65 classifiers. And this was then released to the astronomical community. So this is the sort of standard game. Once we figured out how to do all these things, then it becomes the property of all astronomers, very quickly released. Candel's, as a matter of policy and also NASA rules, releases everything very, very quickly so that all astronomers are able to use it. So this is a little bit of detail on how this worked. And then Mark published the second paper, Mass Assembly and Morphological Transformations, since Redshift 3 from Candel's. We quantify the evolution of star forming in quiescent galaxies as a function of morphology. Our main results are, at Redshift 2, 10 billion years ago, 80% of the stellar mass density of star-forming galaxies is in irregular systems, not disks and not spheroids. These elongated things or things that are hard to classify. However, by Redshift about a half, that's about 4 billion years ago, irregular objects only dominated stellar masses below 10 to the 9 solar masses, much smaller than the mass of the Milky Way, which is about 6 or 7 times 10 to the 10. Quenching. We confirm that galaxies reaching a stellar mass of about 10 to the 10.8, so a little over the mass of the Milky Way, tend to quench. Also, quenching implies the presence of a bulge. The abundance of massive red disks, in other words, galaxies without a bulge, red means quenched, is negligible at all redshifts. So this is the kind of thing you can say when you have access to these classifications of all of these galaxies. So that's how the machine learning made it possible for us to summarize evolution of galaxies in this sort of grand way. Now, what we're trying to do is, what we want to do is, ultimately, I mean, this is our big goal, we have these high-resolution simulations where we know exactly what's happening to the galaxies. We know if a merger event, or maybe a flyby event, another galaxy comes past the galaxy, interacts with it gravitationally, but doesn't merge with it, or some other event that leads to a big inflow of gas in the galaxy. We know those things are happening in the simulations. So what we're going to do is tell the deep learning code what's happening in the simulations and show it images, realistic images that we make from the simulations. And we're making images at 20 different orientations, most of them random, at many, many time steps as these galaxies evolve. So the idea is we'll give the deep learning code all that information and then see if it can be trained to recover that sort of information from realistic images. And of course, if it works, we'll apply it to the real images. And we've already made 100,000 images that we think are typical of what James Webb Space Telescope is going to be showing us, according to our theory. So as soon as that data comes in, we'll be all set to analyze it if this all works. So this was a test to see if we were able to get something right. So Mark Werda's company trained 3 deep learning codes to recognize a bulge in a galaxy, a bulge in a disk, see if we can get a better fit that way, and just a pure disk without a bulge. And so we looked as the galaxy evolved. So each of these is showing the evolution of a galaxy across time, and from higher redshift to lower redshift. And so this is showing where a bulge is, the code says, yeah, that's galaxy's probably got a bulge. And that corresponded to a compaction event where the gas flowed in, a lot of stars formed in the center. So that's redshift about 3.7 or something, and that's consistent with this. And here, bulge plus disk came down, so more bulge, less disk, and at that same redshift, pure disk, hardly at all. And then near redshift 1, about 7 billion years ago, there's this big jump in ex situ stars. That means that another galaxy merged with this galaxy. And so that merger event corresponds to this big increase in the bulge plus disk fraction. And anyway, by looking at this, we're concluding, this was also done for 35 simulations, and we concluded that the deep learning code is sort of working. I mean, it's not nearly as good as we hope to end up with, but this is a step along the way. Another example, so we start with the zoom-in simulations. We look to see if there's a merger, and we looked in a very trivial way, just to see if there's a big jump in the dark matter content. And so we use that, we use the images together with merger or no merger to train the deep learning code. So this was an example of one simulation. Merger here, no merger here, no merger there. And this is what the code did, looking at 20 images at each of many different time steps. So it got this merger. It thought there was some chance of, this is 50%, it thought there was some chance of a merger here when there wasn't. It picked up this merger, and it correctly says no merger here. And this is applied to the simulations, and this is 100% merger, this is the number, and this is basically saying that it's crossing over at about 50% probability of getting the mergers right. So it's not great, but it's sort of beginning to pick things up. Now, this is a completely different project that we're working on. So this is from a paper that, it's a preprint that I'm a co-author of, along with Nicolas Tejos, who's now a professor in Chile, and Aldo Rodriguez Puebla, my former postdoc, who's now a professor back in Mexico City at UNAM, the National University. And what we did is we took a bunch of real redshifts from our big simulation. We divided them into about 20% that we basically used exactly the same redshift. So this is RA, the angle on the sky across, it's like longitude, and it's a thin latitude slice, a thin declination slice. And so here you see there's a void, a cosmic wall, or a filament. And you, with only 20%, you don't see them quite so clearly, but all the numbers are exactly the same. For the photo-Z's, what we did is we greatly degraded the resolution. If all you have is how bright the galaxy is at a bunch of different wavelengths, you can estimate what its redshift is, but it's pretty inaccurate. So this is the photometric redshift versus the true redshift, and you see this big spread. Equality would be this line. And this is what came out after we applied an algorithm that we call sort. And so what we did is we used the nearby spectroscopic redshifts to guess what the correct photometric redshifts were, and you can see we did a lot better. This is true. This is how well we did taking these and improving them using the small fraction of spectroscopic redshifts. This is basically the count of pairs of galaxies, and we basically are getting it right at 4 megaparsecs with this, and with the photo-Z's, the imprecise redshifts, we don't even get it right at 40 megaparsecs. So this is one particular scheme that we cooked up, and we show that it works pretty well, but it's certainly not optimal. And what we're hoping is that with deep learning, we can come up with schemes that will be much more optimal. Now, we're building a fantastic telescope in the southern hemisphere. It's going to be in Chile, called the Large Synoptic Survey Telescope, LSST. LSST is going to take a movie of the southern sky. Every 2 nights, it'll cover the entire southern sky. We discover about 3,000 supernovas per year with all the telescopes in the world. LSST will discover 10,000 supernovae per night. It's 15 terabytes of data per night, which has to be analyzed on the fly. It's sent up to 3 supercomputer centers in the United States. If one of them is down, another one has to be able to step in because you can't allow this kind of data to become too old. So that's going to be several billion galaxies for which we're going to have good photometric redshifts. The fraction of galaxies, we're going to have a few million spectroscopic redshifts. So being able to use photometric redshift data in a more efficient way is going to be critical. And that's why this is a very important project. And then the last project is finding damped Lyman alpha systems, DLAs, in Sloan Digital Sky Survey data. And these are the big lumps of neutral hydrogen in the universe. The amount of hydrogen in the disk of a star-forming galaxy, about 2 times 10 to the 20 atoms of neutral hydrogen per square centimeter along the line of sight. And you see these not because they don't emit very strongly at all, but because they absorb light, especially the n=1 to n=2 transition, the Lyman alpha transition in neutral hydrogen. So a quasar gives us lots of light, and so we look in the spectra of quasars, and about 100,000 quasar spectra were analyzed by hand by many astronomers. And then the most recent project run out of Lawrence Berkeley Laboratory called BOSS provided another 270,000 of these spectra. And so Xiaofeng Dong, who's here in the audience, raise your hand, Xia, and David Park at Santa Cruz, and Professor Exprochaska and Sheng Kai have created a deep learning code that analyzes the spectra and finds these gaps, these places where the light from the quasar has been strongly absorbed. And those are these damped Lyman alpha systems. And so this is basically linear data. It's not an image. And they analyze it in a sliding window. And they've caught a number of these double damped Lyman alpha systems. So this is going to greatly expand the data that's available. And they're just finishing their paper, and they're going to make all of this data publicly available to the worldwide astronomy community. So this will be a huge expansion in the amount of data that's available. And so that's the third use of deep learning. So those are the topics I wanted to talk about, and I think I've allowed plenty of time for questions.
Okay, let's thank Joel for a very interesting talk.
And of course, I'm glad to answer questions about any of this.
Got a mic here I can bring around in case anyone wants to ask a question.
So I know this isn't the focus of your research, but in these elongated galaxies, what's the motion of the stars like in those galaxies?
It's largely along the long axis. There's hardly any rotation at all. The dark matter in these long filaments, remember I showed you the picture of the filaments? The dark matter is supported largely by anisotropic velocity dispersion. In other words, there's a lot more random velocity in this direction than in the 2 perpendicular directions. So the stars are doing the same thing. They're moving randomly in the long axis. And also, suppose that a merger of 2 galaxies occurs. This fairly frequently happens along the filament. The stars are what we call non-collisional. Stars are so small compared to the distance between them that they essentially never hit. So they don't actually scatter off each other very much, unlike the gas molecules in this room, which of course have a pressure. So that's why the stars also, like the dark matter particles, can support this anisotropic velocity dispersion. So that was actually a very thoughtful question, because so we predict that these things are not rotating. And with spectra, we're going to be able to tell. Hubble Space Telescope has only limited spectral capability. But James Webb Space Telescope is going to have superb spectral capability. It's going to be able to get multiple spectra in the same direction at the same time. So we're making detailed predictions. Meanwhile, our same code makes detailed predictions for what the spectra will look like on the ground. Of course, on the ground, the seeing is much worse than because of the atmosphere. But with adaptive optics using laser guide stars, for example, you can improve the seeing. And so there's a limited amount of high-resolution spectral data from the ground. But because of the atmosphere being so noisy in the infrared and not transmitting all of the infrared, James Webb is going to be a complete revelation. So we can't wait to see what we're going to learn from James Webb. And the first proposals for use of James Webb time are already being requested. So the time is going to be allocated very soon. So you know, from the point of view of the astronomy community, James Webb is almost here.
You talk about stars and gas, and that a very small percentage of the universe is stars and gas and atoms and whatnot. What exactly is dark matter and dark energy? Is it subatomic particles, or I'm just not that familiar with this.
We don't know.
Okay.
So I was the one who first proposed, along with the late Heinz Pagels, that the favorite theory of theorists in particle physics to go beyond our current understanding would also be the explanation of the dark matter. So the standard picture of particle physics is called the Standard Model. And back when I was a graduate student and in my first postdoc, my postdoc at Harvard, I actually wrote some of the basic papers on what we call the Standard Model of particle physics. It's the theory of the electroweak interaction. Now we know the weak interaction is closely associated with electromagnetism, and also the strong interaction, which is a similar kind of theory, non-abelian gauge theory. And the trouble with that theory is, although it beautifully describes all the results at particle accelerators, there's no room in it for dark matter. And moreover, we have no idea where the theory came from. I mean, we can write it down, but why does it have the particular structure that it has, we don't understand. So we're looking for a bigger theory that this theory will just be a part of, the Standard Model. And the best candidate is supersymmetry. And supersymmetry is the basis for string theory. It's actually superstring theory. So if you've heard of that, that involves supersymmetry. So in supersymmetry, all of the particles, all the fundamental particles, the quarks, the leptons, the force particles, the photon and its partners, the W and Z bosons and the gluons, all of those particles have partner particles whose properties, except for their masses, are totally predicted by the theory. Their interactions are totally predicted. The masses arise from what we call symmetry breaking, and we don't know how that works. So the masses can't be predicted. But we know that the masses must be much higher than the masses of all the ordinary particles. We haven't made them yet at accelerators. So that's supersymmetry. Now, in most versions of supersymmetry, the supersymmetric particles have a different quantum number called R parity, negative R parity. All the ordinary particles, positive R parity, and parity is conserved. So the lightest R parity odd particle must be stable. And so it should be the dark matter. That was what we pointed out in 1982. And that led to the cold dark matter theory. So that's a plausible story. It hasn't yet been ruled out, but we also haven't found the particle. If it exists, we should start making these particles at the Large Hadron Collider in Geneva. And they've been turning up the intensity, and they may, in fact, be able to increase the energy a little bit. We're on a big run and much higher intensity. Maybe we'll actually start to see something. My colleagues at Santa Cruz were part of the team that built the inner tracker for the Atlas detector at the Large Hadron Collider. But they don't tell us anything. They're over in Geneva, and they're working on the thing. But when they discovered the Higgs boson, we learned about it just like everybody else did. We didn't learn about it from them. So they may even have some results, but if so, they haven't told us. We're also looking for these particles deep underground. You go deep underground to shield from cosmic rays. The most sensitive detector until recently was the LUX detector, Large Underground Xenon, and the Home State Gold Mine in South Dakota. My wife and I, we've written popular books on this stuff. Those images from the beginning of my slides were from our books. And we were the speakers at the South Dakota place. In fact, we gave a National Public Radio interview deep in the mine. That was a couple of years ago. And they announced, when they introduced us, the Department of Energy people announced that they've made a commitment to drastically expand the LUX detector. So LUX was 300 kilograms of liquid xenon gas, and they're expanding it to 8,600 kilograms, 8.6 metric tons, which will be an increase in the sensitivity of a factor of 100. So if the dark matter particle is what we suggested, which is often called a WIMP, a weakly interacting massive particle, they should detect it. If they don't, they'll rule out the theory. Meanwhile, a 1,000 kilogram detector is going into operation in Italy this year. So there'll be steps along the way. If these particles are the dark matter, they should annihilate sometimes into gamma rays. There's a signal of gamma rays coming from the center of the Milky Way, but it's not clear if that's it's distributed just the way you'd expect it to be if it's coming from dark matter annihilation. The dark matter particles annihilate. Two of them have R parity even, so they can annihilate into ordinary matter. But there are other possible explanations. So the assumption is that the dark matter is some kind of particle. Sorry for all that introduction, but partly because I'm responsible for part of it. I sort of live this stuff all the time. Of course, I'm hoping that it turns out to be what I predicted, but we don't know. As far as the dark energy, it's even more mysterious. Einstein, in 1916, applied his theory of general relativity, which he'd finished at the end of 1915, to the universe, and he discovered the universe has to be expanding or contracting, can't be static. And he asked his astronomy colleagues, so is the universe expanding or contracting? And they basically said, we don't know. They didn't even know there were galaxies outside the Milky Way. That was controversial. It wasn't until Hubble in 1924 showed that the Andromeda galaxy is far outside the Milky Way that we knew that galaxies are an external phenomenon. And then in 1929, Hubble discovered that the more distant the galaxy, the faster it's moving away from us. So the universe is actually expanding. In 1916, nobody knew these things. But Einstein was motivated to try to come up with a way to make his theory static. So he realized you could change the equations by adding an extra term that he called the cosmological constant, represented by lambda, the Greek letter, and that would be a repulsion of space by space that he thought could counteract the attraction of mass and could make a static universe. It turns out it doesn't work. But when we discovered that the universe is actually accelerating the expansion using type 1a supernovae, the Nobel Prize a few years ago, that basically resurrected the cosmological constant, or some other form of dark energy. We realized that we can add this to Einstein's equations. It's perfectly consistent. Is it some fundamental new aspect of nature? Is it a consequence of something else? There are ways that you could construct it so it's a consequence of something else. We don't know. So one of the biggest projects in astronomy today is the dark energy survey and the dark energy spectroscopic instrument. And these things are led partly by people here in this area. My former graduate student, Risa Wexler, is the spokesperson for the Dark Energy Spectroscopic Instrument, DESI, at Stanford. So this is big astronomy, and the Large Synoptic Survey Telescope that I mentioned, and it's going to go into operation in Chile, the Southern Sky every 2 nights, that's largely funded by the Department of Energy. Mike Turner, an astronomer at Chicago, coined this term dark energy. And it was a brilliant term because the Department of Energy has taken on funding unless the Trump administration kills it, because they want to basically drastically curtail science in the Department of Energy. So I don't know.
Should rename it fake energy.
So what's the evidence that black holes, either for or against, that black holes are in fact dark matter, primordial or otherwise?
Primordial black holes could form in certain versions of cosmic inflation theory, sort of the early stages of the Big Bang. But it's very, very tricky. The danger is you make too many, and then it wrecks the whole universe. They have to be, if they can't be too small, we'd see them exploding. It turns out black holes explode, and so they have to be in a very certain mass range. They can't be exploding, we would have seen that. And if they're as massive even as Earth's, we would have seen the effects because they would have amplified the light from supernovae, and they would have given us a tail of extra bright supernovae that we don't see. So there's strong constraints on the mass of any dark matter candidate that's a massive sort of object. Machos is one of the names people call these things, massive compact halo objects. One of my former graduate students introduced that terminology. But that's been largely ruled out. So it's very unlikely, I think, that the dark matter is black holes. Also, well, I can go on that. So there's two kinds of black holes we are quite sure exist. The kind that form at the ends of the life of massive stars, and the kind that we see at the centers of all the massive galaxies, which we call supermassive black holes. There's no question they exist. And of course, the best proof that there really are these massive black holes that are in the stellar mass range was this discovery a couple of years ago by LIGO, Laser Interferometry Gravity Wave Observatory, of two merging 30 solar mass black holes. And the pattern of gravity waves was exactly what Einstein's theory predicted. And we had previously been testing Einstein's theory at scales in the solar system. The velocity of the sun is 30 kilometers a second. The speed of light is 300,000. When those two black holes merged, they were going around each other at essentially the speed of light. So we were testing general relativity at the limit, and it was bang on. Incidentally, two 30-mass black holes merged, and we got a 58 solar mass black hole. Two solar masses, 2 times the mass of the sun, was gravity waves. So, and now they're detecting a lot more. There's going to be a public talk by Gabriela Gonzalez, the spokesperson for LIGO, in Santa Cruz this Thursday night, June 1st. And she's a wonderful speaker, incidentally. You guys should invite her if you want to have a wonderful talk. And they're now souping up LIGO so that it can detect about a third the intensity that they detected before. That'll let them look 3 times farther out, and that's 3 times in every direction. So that's about 27 times the signal rate. We've been getting about 1 detection a month when they have the thing on, and that's going to turn it into 1 a day. So we're going to learn a lot more about black holes. But I don't see any evidence at all that black holes are the dark matter, and we're going to learn much more about black holes, both on the stellar mass scale, and then also if we can put a detector in space. LISA was the name. The Europeans want to go ahead with it. If the US will join, we could do it much faster. And so that'll let us detect merging black holes of the masses that we find in the centers of galaxies. And that'll give us a much better census on those. Anyway, the whole black hole story is very much a hot research topic, especially with LIGO.
I was wondering where the dark matter is or how it's spread across the Milky Way, because you said there's a massive halo of dark matter. How is it that we don't see the effects of this dark matter or dark energy on things like the solar system, right? The orbits that we see, probably, would they match the mass of the sun? So does that mean that either there's no dark matter in the solar system, or does it mean that part of the sun's mass is dark matter or dark energy or something like that?
Wonderful questions. Those are all subjects of many articles in the scientific literature. So the basic story is that the dark matter is not the dominant component of mass in the inner part of the solar system. If you remember those pictures I showed, in the early stages of galaxy formation, the dark matter is dominant all the way to the center. Then gas flows in, turns into stars, and the dark matter is only dominant on large scales. So on the scale of the solar system, ordinary matter is by far the main source of mass. The solar system is enormously more concentrated mass than you find just if you spread out. If you look at the mass on large scales, even in the Milky Way, little planetary systems like ours are very, very dense compared to the average. So the dark matter would have very little, would make very little difference on the scale of the solar system. You know, we've worked that out. The amount of dark matter is about 1/3 of a hydrogen atom per cubic centimeter. That's about the mass of dark matter in the Milky Way at our distance from the center of the Milky Way. So that's less than a very high vacuum. The solar system has a lot more stuff than that. But as you go out to the edges of galaxies, it becomes the dominant form of mass. So very little effect on the solar system, but it's possible that the sun and the Earth and Jupiter and so forth will have accreted a certain amount of dark matter. If so, that dark matter would end up in the center. It would occasionally collide with atoms and lose energy and end up in the center. And the dark matter would start annihilating, if it's the kind that I predicted. And there should be neutrinos coming from the center of the sun. And we've looked for them and we haven't seen them yet, but we haven't looked with very high precision. So this is one of the ways that people are looking to detect dark matter. It's very lively, and so all of those issues that you raised, the questions you raised, are exactly the kinds of things that we've been thinking about very hard for decades.
And thank you all again.